So today we're going to talk about moment of a force. So just a quick definition. So non-concurrent forces that cause a body to rotate about an axis is what a moment is. Non-concurrent, of course, meaning not on the same line of action. So this may also cause bodies to bend and twist. A moment has two main components, so the magnitude and the direction of the force which causes the moment, and the perpendicular distance, the moment arm, from the point of interest, which we can call d. So the moment is equal to p times d. So this means that the moment about point O is equal to the magnitude and direction times the distance, in which the moment is defined by a Newton meter. So the effect of a moment will be unchanged if transmitted along its line of action. So if you move the force along the line of action, then it won't change. Same thing with a moment. It will not change if moved along the line of action. And the moment arm, just remember, is perpendicular to the force's line of action. So just some principles of moments. The moment about point O is equal to the sum of the moments of the force's components about O. So, for example, this comes in useful for strange shapes. So we only have to consider the moment arm, and we can ignore the shape itself. Direction of moments. So moments may be drawn as double-headed arrows. And just as a convention, so the right-hand rule, if the thumb is a moment vector, the fingers on the right hand curl around in the direction of motion. So if you stick your thumb out, that will be your moment vector, and you have your fingers curling around. That will be the twisting motion or the rotation caused by the moment vector. Some sign conventions. So counterclockwise is positive and clockwise is negative. So solving for moments, first you want to find the force, F, which is causing the moment, and express it in Cartesian vector notation. Then we want to find the position vector from the point of rotation to a point on the line of action of the force. And finally, we want to calculate the moment using the cross product. To find the moment of a force about a specific axis, first we want to find the moment about a specific axis rather than a point. So this can be used on something like door hinges or anything like that. So first we want to find the moment on a point on the axis of rotation. And then we want to find a unit vector along the axis of rotation. And finally, find the dot product of the moment and the unit vector. So we're going to do a video example, which is just in 2D. So we have an object here whose center is B, or at least the axis of rotation is B. And if we label B as the origin and A is the point at which the force meets the objects, then the point A has the coordinate 2, 2, and the force F is directed along a line of action 65 degrees above the horizontal and has a magnitude of 60 newtons. So that's our video example, and then we'll also do an extra example, which will be posted online in the description, which is about moment about an axis. But we'll start with this one. So what we want to do first is define the force in Cartesian vector notation. So we know that the force is equal to 80 newtons, and it's 65 degrees above the horizontal. So just to redraw this again, we have the force something like this, and this is 65 degrees, and the force is equal to 80 newtons. So in this case, the force only has x and y components, so we can say that the z component is 0. Find the x component. Just going to grab a calculator for this, because this I didn't choose the numbers such that they'd be particularly easy, but So the x component will be 80 cos 65 degrees, which is equal to 33.8, but of course it's negative because it's pointing in the negative direction, so negative 33.8. Y, similarly, we have 80 sine 65 degrees, which is equal to 72.5. And since it's pointing up, then it is positive, and these are in newtons. And then Z, we have just 0 newtons. So then we want to find a unit vector for this. So what we'll do for this is, okay, so we have our force here. And actually, for this one, we don't need a unit vector. We already have the components of the force. But if the question were to give you a direction of the force in terms of the Cartesian vector notation, then you'd find a unit vector, multiply 80 by that unit vector. But anyhow, we found it a bit of a different way, so I'll just write it out here. So force is equal to negative 33.8 I plus 72.5 J plus 0 K. Okay, so then we want to find the position vector from the point of rotation to the point on the line of action of F. That's fairly simple to find, so I'm going to call that R. Then what do we have? Oh, sorry, I'll go back to this. So from B to A, so say R, B, A is equal to, well, 2, 2 minus 0, 0, which is equal to 2I plus 2J plus 0K. So we have our force vector, and we also have our position vector. So we can go ahead and put that into our matrix here. So we have I, J, K, and then we're going to put in our position first. So that's our RBA. And then our force. And I should denote these as vectors. And I just want to spread these out a little bit as well, just so we have room for significant digits. So we have 2, 2, 0, and negative 33.8, 72.5, 0. Okay, and then we're going to find this. So I'm going to call this moment about B is equal to So what we're going to do is we'll do the steps that we did last time. So for I, and go back to the cross product video, which is the last video, if you need a refresher for this. But I is going to be 2 times 0 minus 72.5 times 0. And then minus, so for j, it'll be 2 times 0, minus negative 33.8 times 0. So far we're getting pretty easy numbers. But then we'll do k, so we'll have plus, and then 2 times 72.5 minus negative 33.8 times 2k. So then our moment will end up being 0i minus 0j, I guess we could say plus 0j, and then I'm just going to figure this out, minus, so if my calculations are correct, then we'll have 212.6k, and I believe that's all we need to find, yes. So this one was pretty simple just because it was only in 2D, so since it was only in the x and y directions, then we get a turning force in the z direction, in that k direction. So that's it for this video. I hope you enjoyed and I hope it helped. Thank you again to Loom and Google Keep, and as well to my professors, and thank you for watching.